much. Usually when I start a talk, I used to thank the organizers generally, but now I am one of the big set of organizers, so I want to specify my acknowledgement. I really want to thank you, Ivan and Jana, because you really did a great job and you still are doing a great job, so thank you.
Thank you.
Well, in this talk, I'm going to present a joint work with Stefano Bonaccorsi, Craig Calcaterra, and Mirko Dovidio on the probabilistic representations of high-order type equations. Actually, just a moment. Let me switch here. Okay, this is the plan of the talk. So first of all, I will introduce the problem showing what kind of technical difficulties one has to face when one wants to construct a probabilistic representation, let's say a Feynman-Kac type formula for the solution of evolution equation which do not satisfy maximum principle. And in the second part of the talk, I shall focus on a particular toy model, which are the so-called high-order type equations. The most famous example is the equation associated to the so-called bilaplacian, but we will consider more general partial differential equation of any integer order n of this form, and I shall show you how one can, let's say, circumvent the difficulties I'm going to describe in the first part of the talk and construct a probabilistic representation for the solution of this particular partial differential equation in terms of a sequence of very simple random walks on the complex plane. Our starting point is the celebrated Feynman-Kac formula, very, very famous, introduced by Mark Katz in 1949. Mark Katz was inspired by a lecture held by Richard Feynman at Cornell University on Feynman-Path integrals and realized that it is possible to prove for the solution of the heat equation with sink, with a potential V, let's say, a beautiful probabilistic representation of this form given in terms of the expectation with respect to the distribution of the Wiener process of equivalently as an infinite dimensional integral on the space of continuous paths with respect to the Wiener Gaussian probability measure. And it turns out very soon that this formula is a very rich source of powerful results and techniques. And according to the words of Mark Katz himself, who said the formula and its many enclosed and distant relatives are proven to be useful and sometimes powerful tools in a variety of problems. Hardly a month passed without someone discovering yet another application. And actually, nowadays, Feynman-Kac's formula is just the main, first, and most famous example of an extensively developed theory which connects analysis and in particular partial differential equation with probability theory. In particular, it allows to represent the solution of parabolic equations associated to second order elliptic operators, two stochastic processes, solution of a stochastic partial differential equation of this form in such a way that the solution of the evolution equation can be represented in terms of the expectation with respect to the distribution of the stochastic person by means of this Feynman-Kac type formula. And it is interesting to point out that this kind of representation, which is actually very useful, extends to different kind of partial differential equation. For instance, we can consider the case of fractional derivatives. So the case where the Laplacian, or more generally the second order elliptic operator, is replaced by a Fourier operator with this kind of symbol. Even in this case, it is possible to prove a probabilistic representation for the solution of the associated evolution equation of this form, again, where the expectation now is taken with respect to the distribution of a Levy process, H alpha, which is called alpha stable subordinator, and it is characterized basically by this particular form of its Laplace transform. And by using the theory of Bochner subordination, one can extend this kind of result to the fractional derivatives of the Laplacian in this way. So we can even consider evolution equations where the fractional derivative of the Laplacian appear and construct a probabilistic representation by composing the Wiener process with the alpha stable subordinator, which plays the role of a stochastic time of the Wiener stochastic process. Well, all these nice results fail in the case we simply replace the Laplacian with some integer power of it, and we consider, for instance, an high-order E-type equation of this form, or again, if we simply multiply the Laplacian by the imaginary unit, we obtain the famous Schrödinger equation. Here we are. In both cases, it is actually impossible to prove a Feynman-Kac type formula, namely a representation for the solution of this form here, given in terms of the expectation with respect to the distribution of a whatever stochastic process with real paths. And the main reason for this no-go result is quite simple. Indeed, the solution of both equations do not satisfy maximum principle, which would be basically implied by this particular representation for the solution, at least for suitable potentials. But, however, many mathematicians try to solve the problem and try to, let's say, provide a kind of functional integral representation for the solution of equation of this form. Let me point out that in the case of the Schrödinger equation, these problems actually coincides with the problems of the mathematical definitions of Feynman path integrals. But if we want to have a, let's say, deeper insight in this no-go result, we can look at the traditional Feynman-Kac formula and see what works in the case of the heat equation, which cannot work in the case of Schrödinger equation or high-order E-type equation. So let us consider, as in the talk of Ivan Trapasso, the Trotter product formula. Now we want to study the semigroup generated by the operator sum, the semigroup on the Hilbert space L2 of R, generated by the operator sum of a multiplication operator associated to a potential V that here we assume to be continuous bounded, but this assumption can be relaxed. This is not the problem actually. And an operator A, which is assumed to be a generator of a semigroup, and in our mind can be either the Laplacian or some higher power of the Laplacian, or the Laplacian times the imaginary unit. In the first case, we have heat equation. In the second case, high order heat equation. And the last one, we have Schrödinger equation. By using Trotter product formula and by representing the action of the, let's say, free semigroup, the one without potential, in terms of a kernel, integral kernel G, and by inserting this representation in the formula coming from the Trotter product approximation, we have such a convergence result. Actually, the convergence is strongly in L2, but by taking a subsequence, it holds for almost everywhere X in R. And this gives the solution of our evolution equation as the limit of a sequence of finite dimensional integrals of this particular form. And now one can look at this expression as the cylindrical approximation of an integral, infinite dimensional integral, with respect to the distribution of a stochastic process with the Markov transition kernel given by the kernel G, and by taking the limit, one gets formula this kind of probabilistic representation, this kind of Feynman-Kac type formula. But I want to point out that this last step, the final part, is allowed provided we are able to construct this process, or equivalently, if we are able to construct on the space of real valued paths a measure whose value on the cylinder sets is given by an expression of this form, where G here is the kernel of the free semigroup, the one we introduced before. Now, in the case of the heat equation, G is well known, is the density of a Gaussian measure, and in this case, the Kolmogorov existence theorem assures the existence of the measure mu we were looking for. In other words, this expression, which gives a finite additive measure on the algebra of cylinder sets, can be extended to a sigma additive measure on the sigma algebra generated by the cylinder sets. But in the case of the Schrödinger equation or higher order E-type equation, we have an explicit expression for the kernel G, which is given by this formula here in the case of Schrödinger, and by this Fourier integral in the case of the higher order type equation, and both functions are no longer real and positive. In the first case, we have a complex function, and in the second case, we are a real value function, yes, but which changes sign an infinite number of times. And those functions, when looked in this particular definition, play the role of the density of complex or sign measure. This means that Kolmogorov theorem does no longer apply, and this feature is fundamental because it is on the roots of a no-go result proved for the first time in 1960 by Cameron in the case of the Schrödinger equation, and by Krylov in the case of high-order E-type equation. Actually, the measure we were looking for cannot exist. Indeed, if it existed, it would have infinite total variation. This means the following, that we cannot prove a representation formula for the semigroup of this form given in terms of an integral on the space of real value path with respect to a sigma additive measure mu, which has this form on the cylinder sets. And despite these are no-go results, it actually triggered in 1960 a huge research activity in the mathematical community. Many mathematicians started to try to solve this problem and to propose different approaches to the construction of an integral representation for the solution of those equations. And many approaches have been proposed. I have no time today to list all of them, but I would like to show you a rather simple approach which allows to handle the case of high-order type equation. Let us consider again traditional equation, this one here, and its probabilistic representation, Feynman-Kac formula in the case of vanishing potential. And let us recall that by Donsker theorem, it is possible to construct the Wiener process as the weak limit of a sequence of very simple random walk on the real line. In this way, when you fix the time variable t, it is actually a consequence of the central limit theorem. Hence, we can, for the solution of the equation, write down a representation formula of this form as the limit of the expectation with respect to the distribution of the random walk. Why not? This is exactly the formula we are going to generalize to the case of high-order type equations of this particular form, where now the degree n of the space derivative can be an arbitrary positive integer, and beta is allowed to be a complex parameter. And we will construct a sequence of random walks of the complex place which allow to represent, at least for suitable initial data, the solution of the evolution equation by such a limit. Our starting point is the construction of a sequence of independent, identically distributed complex random variables. In particular, they are assumed to be uniformly distributed on the sets of n roots of identities suitably multiplied by the n root of the parameter beta. Just to give you an idea, here in this picture, I have drawn the red points where the random variable xi are distributed, are concentrated, their distribution is concentrated in the case beta is equal to 1 and n is equal to 3, or beta is equal to 1 and n is equal to 4. Okay, this complex value random variable has this interesting property. They complex moments exist, but they vanish unless the order m here is a multiple of capital N. In particular, for instance, when n is equal to 3, this random variable has vanishing first and second moment. The third moment is equal to beta, the fourth is equal to 0, fifth is equal to 0, 6 equal to beta square, and so on. And this is the starting point for the construction of our random walk on the complex plane, which is defined in this way. The independent steps are given by these discrete complex random variables. And here we have this particular scaling exponent, which is relating to the order n of our partial differential equation. And given this quite strange definition, we are able to prove this convergence result. If we compute the limit of this expectation, the expectation of imaginary exponential of the random variable Wn of t, we obtain exactly this formula. In the limit, this stochastic process seems to behave as an unstable process. But these results deserves some comments. Indeed, well, in the case n is equal to 2, we have the traditional equation, and the sequence of processes converge to the Wiener process. But when n is strictly greater than 2, which is the interesting case, the sequence of processes cannot converge weakly because of this particular scaling exponent here. In other words, there cannot exist a limiting measure on the space of complex value path, which is the weak limit of the sequence of measure mu n, which are the distribution of this sequence of random walks, complex value processes. So this result has to be interpreted in the following way. Even if we do not have a limiting measure, the limit of integrals of suitable functions, in particular the exponential functions, with respect to the sequence of measures exist. And that's it. And even if these convergence results seem to be quite weak, but we cannot expect much more in view of what I told you at the beginning of the talk, this is sufficient for the construction of our probabilistic representation. Indeed, if we consider for this particular initial value problem associated to the high-order type equation, an initial datum which has this form, it is assumed to be the Fourier transform of a complex bounded measure on the real line with compass support. Then, in this case, we can prove that the solution of the equation can be computed as the limit of this expectation with respect to the distribution of the random walk on the complex plane. And this result can be generalized to the case we consider also a perturbation with a potential which is linear in the space variable and it has a continuous dependence on the time variable here. And still we have a representation for the solution of this form. This result paves the way also for the description or corresponding representation also of the partial differential equation associated to any fractional derivative of the Laplacian. In particular, we can consider evolution equations associated to a fractional derivative operator of this form, where this expression actually is meant as the Fourier operator with this particular symbol here. In this case, we can use the technique of Bochner's subordination and we can construct a sequence of processes on the complex plane which are obtained by composing the random walk on the complex plane associated to the n-order differential operator I described before with a sequence of compound Poisson processes converging weakly to the alpha stable subordinator. And by introducing this particular sequence of random walks with scale time in the complex plane, again, we have a probabilistic representation for the solution in terms of this particular limit. And again, by using Bochner's subordination, this result can be extended to the case we have an order derivative with respect to space, and here we have a fractional type derivative of Caputo type. Indeed, again, by considering a stochastic process with complex value path defined by composing the sequence of random walks on the complex plane associated to the n-order differential operator and a random time, in particular here we have to choose the so-called inverser of the subordinator, we still have a probabilistic representation for the solution of this kind of a fractional evolution equation in terms of the limit of the expectation of with respect to the distribution of this particular process. And if you need additional details, here are some references. I think that I can stop here. Thank you for your attention.
Yeah, thank you very much. Yes, we should actually thank the speakers. So we didn't do it first time, but we will thank all the speakers after the session. So are there any questions or comments? Well, in this case, I guess I have to comment.
A question.
Yeah. Welcome.
Sal-of-Cost has some results on similar random walks with a lot of cancellations, like vanishing moments. In particular, that they have estimates of let's say, transition kernels. Do you also give some estimates?
On the transition curve, actually limiting process, but we have just a sequence of very simple processes which actually do not converge, but we have some descriptions of the behavior of these processes when n increases, and it is quite an odd behavior, because you expect that something wrong is going to happen, right? In particular, when n increases, you have that your process exit from any ball in finite time. And so we do not expect to be able to, obtain nice estimates on the kernels. Some estimates which can give you some nice behavior. I think so.
That's intriguing topic. Of course, many people were interested in that. For instance, I remember an old paper by Helms. He solved the biharmonic equation in a ball by putting some extra boundary conditions, which probably kills these oscillations as you leave the ball. Because of course the problem is with those oscillations that are created somehow all the time. So anyways, that's very interesting.
Yes, but many, I would say, very good mathematicians propose a very different solution for this problem. So starting from Krylov, Funaki, some times ago, I guess that even Terry Lyons proposed a solution, conjecture that rough path theory could give some insights in the construction of the measure, which is ill-defined here, but according to his conjecture, rough path theory could allow a good definition of this non-existing measure, as I told you. So there is a huge research activity, which is, in my opinion, parallel to the research activity concerning mathematical definition of Feynman path integrals. The two communities somehow are tangent, and in some cases they have connections.
Yes, yes.
Right. The problem is the limiting object. Maybe we could do without the limit. Just consider the approximations. By the way, do you have any interesting martingales using those random walks that you use?
So can you repeat the question?
Is if you are using some interesting martingales to analyze those random walks.
No. It's very, the analysis of this random walk is quite simple. When n is finite, you just, use simple results on the theory of Markov chains. And the problem is that you are not able to take the limit for n goes to infinity, but it is a very, very simple process as soon as n is finite. That's, I think, that's the point of the result, because it also suggests that somehow you can construct a numerical approximation for the solution via Monte Carlo technique, because the process is very, very simple.
Indeed. Thank you again.
Thank you
for your question.
I also have a couple of remarks. As Sonia has mentioned, there are many approaches to solve such type of problems. Yeah. And in particular, I guess there is a guy, Arzinger, who together with Davidio and other people from Italy made some progress by relating higher order derivatives in the space to fractional derivatives in the time. Yeah. So then there is a kind of duality. So you can, so roughly speaking, reduce the order in space by making some other order in space in time. So just changing this order between time and space, and then one can use some stochastic representations for time fractional evolution equations. So I have mentioned some in my talk on Monday. So you're welcome to listen it at YouTube. So this is one remark. So roughly speaking, there is a Feynman-Kac formula, but not that direct.
Yes,
and another remark is that there is also Feynman-Kac formula for Schrödinger equation in terms of Brownian motion, made by DOS. So using this square root I multiplied with Brownian motion, but still again, Feynman-Kac formula is available, local in space, in time, but nevertheless it exists. Yeah, so they were just remarks.
Okay.
Remarks. So are there any further questions or remarks? It seems to be not the case, so let us thank the speaker again.
Thank you.